So who in the room is a Java developer? Okay, this is 100% in this group, okay? As calibrating myself. So that was not everybody, that was interesting. So who has ever done any kind of Haskell, Miranda, OCaml, ML, Cecil, Opel, something? So this is like, okay, half of the audience, which is interesting because I assume if you dislike this kind of language with a passion, you would not be here. So I assume that you like it, which is good. And I assume you want to see how it would work on the JVM, or it can possibly work on the JVM maybe. And when I started my endeavor, when I looked into Haskell, my impression was that I'm the only one on the planet that does Java and Haskell at the same time. And I'm surprised and I'm pleasantly surprised to see that there's an overlap. That, of course, we are addressing with Frege. But also we are addressing the second group. So people that have not yet seen these languages and are kind of curious on what is different. We will focus also on, in the first half of the talk, on what is different. That's me, Dierk König. I work for Canoo in Basel, Switzerland. To begin with, and particularly for the second group that has mainly done imperative programming in the past, I'd like to read you a program. And I'll ask you what that program does. Okay? That's kind of a challenge in the afternoon, a little bit. 5 lines of code contains 3 variables, A, B, and C. And when I say A equals 1, that has value semantics, meaning that the value 1 gets assigned to the variable A. A equals 1, like written, you know? Okay, is that okay for everybody? So here's the challenge, 5 lines of code. A equals 1. Got it? B equals 2. C equals B. B equals A. A equals C. What is that code doing? Somehow, I guess my where is that? The other side. It's getting worse, you know. When you try to optimize, it gets worse. Does anybody have a shaver with them? So anyway, so ideas, what the program was doing. Flipping 2 values. Very good. There was somebody in the audience. So I'll now give you a mind read of what your mind was doing when trying to follow this program. So now comes the engineering part. I'm going to need this for the live coding. Anyway, so you have to cope with that, I fear. Good. So A equals 1, so there's a memory location for the variable A, which now contains 1. B equals 2. Here you go. C equals B. Okay, A and B stay the same, but then the value from B gets copied over to the location C. B equals A, so A and C stay the same, but then the value in the location of A gets copied over. A equals C, so B and C stay the same, but what was once copied over, which was initially the value of B, now gets copied over to A. So this is the steps that we have to follow. We follow in our head. We follow these operations, and as engineers on the Java platform, mainly using imperative code, this is the kind of reasoning that we apply every day. We are also a self-selected group, you know. People that have immense difficulties doing this kind of mental juggling, they don't stay in programming very long. It's too frustrating for them. But I guess you also agree that for this rather primitive operation of flipping or swapping to values, the number of steps and the amount of considerations that we have to do is rather high. The price is rather high for little outcome. And this is because not only do we have to care about 3 different places, our brain is rather good in caring about places, but the brain is not very good in caring about these places at various points in time. And why do we have time at all in this thing? This is because of assignments. Assignments introduce the notion of time in code. Everything that happened before the assignment and everything that happened after the assignment. This is where you get the time into the equation here. And that means that even for this primitive operation, we have to care about 9 different states, as you see here. The initial ones over here is just a definition, but then we have 9 different states. The short-term memory of the average human, and I'm pretty sure you're above that number, is 9. You can manage 9 places. The average is 7, plus minus 2, minus 5. And if you try to remember what happened to you when following my lines of code, I assume that somewhere here or here, your mind gave up. This is how you can judge, you can estimate how big your short-term memory is, because that's rather difficult for the brain. And only a few brave ones have followed through. So, thumbs up to you. You just guessed, that's also fine. Good guess. So this is, and because we have to follow these operations to reason about the code, this is called operational reasoning. Now, if this small thing is already rather difficult, so difficult that most of us cannot do it in the head, we need some tooling support for this. You know, we need tooling support that gives us information at what point in time our memory locations had what value, and this is called the debugger. The main reason, by a far margin, the most important reason for a debugger is this, the notion of time. Location-based programming and the notion of time combined. If you don't have that, there's dramatically less to do for a debugger. And I guess you've already been there, so you make a watch variable on one of those, and then you single step through it to see what unfolds in the operation. Good. I have recently explained this to my parents. My mom is 75 years old, my father is 80 years old, and they have no technical training whatsoever. And they asked me, boy, what are you doing? And I said, well, you know what? This coffee cup over here is an A, and this glass of water is a B. And then we want to swap that over. I cannot just put that in that. No, that also doesn't work. So my father said, you have to have temporary storage over there. I said, that's just like a programmer, yeah? And move that over and this over here, and then juggle that around. And we do this in our head, I said. And my parents had this face of, oh, poor boy. This explains something. And but yeah, we figured something out. Currently, with this new thing, we have a new idea. We call it functions, and it works like so. We put this coffee cup over here, and we have this glass of water over here. And then we leave it like so. And never change it again. And whoever looks at this thing always sees a consistent state. Done. Case closed, you know, by definition. And then my father said, yeah, but boy, you said you want to see it swapped over, right? So I said, yes, seeing it swapped over is easy. I took his glasses and said, just imagine you have these prism glasses where, you see the left to the right and so, right? There's those glasses on the internet if you want to. And then you see it like so. But this interferes with nobody. You can have 1,000 people looking at this information, and everybody has different glasses. One is only looking at the first value, and then the second value, and one has only +1 filter on, and nobody interferes with anything else, with anybody else. And there's always a consistent state. That's much easier. If I would have told you in the beginning A, B equals B, A, you would have guessed quicker what the code is doing. Pretty sure about that. So we have a new idea. The new idea is we just get rid of these assignments. They seem to be dangerous. And assignments are just a special incarnation of statements. So we just, in one go, statement also ruled out. Now, if you don't have statements in a programming language, you also don't need control structures anymore, because control structure control the flow of operations, and you don't have operations anymore, no statements, so you don't need control structures. So from tomorrow morning on, we do programming differently. No assignments, no statements, no control structures. How would that be? This would that would be different. Question is that practical? Can we really do it? And there's actually two ways of doing it. The blue pill and the red pill. The blue pill, if everything that, I like this track very much in the conference. It was a very good track, interesting content, lots of insight about programming, most of it functional programming these days. But the blue pill, it was the blue pill that we have seen so far, imposing developer discipline. Who has been in the first talk this morning in this track? Some, yeah, okay. Telling, well, the ongoing, the repeating statement was, and then we settled on a convention of only doing this, and then we settled on the convention of never doing that. So, and this kept us on track for functional programming, You have to impose discipline one way or the other, maybe tool supported or to some extent language supported in other languages. But the only language that gives you the red pill, where you get rid of the old metrics thing and you enter the new world of reality, is using a purely functional language that doesn't even have a notation for assignment. There is no syntax for assignment. You cannot do assignment because there's no syntax for it. There's no syntax for statements. There are no control structures in the language. So this kind of forces you into a new way of thinking, and using a new programming language or an alternative programming language only makes sense if it forces you to think differently about your solutions. It's not about superficial syntactical differences. The superficial syntactical differences that we'll see today are only there to remind you of the fundamental underlying differences. And here is our idea for a purely functional language. I'm going to show you some code. If you want, you can follow the code samples in online. There's an online REPL read eval print loop where you can try that code. I'll show a little bit of code here. Later I'll do a little bit of live coding to give you the joy of seeing me failing and so on. Good. So, and by the way, for the non-German native speakers, the word Frege is a bit difficult to pronounce, so you're entitled to call that freaky if you want to. So, here it comes. We are working with functions. All our code is built from functions. The whole language is built from functions. No surprise, there's lots of language support for functions, because it's all it does. And here's how you define one. So in the REPL, let's say we define a function called times. It takes two parameters, a and b, and returns a times b. This is how you define a function. It looks somewhat unfamiliar. First, from Java perspective, first we don't see any types. Is that kind of untyped or dynamically typed? What is it, kind of just JavaScript-y thing? No, as we will see. How do we apply a function? Well, we can just give the parameters like so in the most silent fashion that you can think of. The operator for function application is space. And this is actually the theme of this conference, is going to new spaces or something. So that is, we are using space here, going to space. I like the keynote so much. It's the best keynote that I've ever seen. So we are using space here. So this space over here is actually an operator that takes this function and applies it to this argument, and then to the next argument. We'll see how that looks like in a second. So no surprise, it returns 6. And we can ask the REPL for the type of times. As I said, there is some type. It's not untyped. And the type looks somewhat crazy. We'll see what that means in a second. Let's get some help. So we had no times declared. The types are inferred. We did not even declare the types of the parameters. Frege and Haskell have global type inference, meaning if you don't want to, you almost never have to write any type. But no matter how small or big the expression in your language is, it will always be fully type inferred. So I said that this space over here, of the blank character, is denoting the function application operator. Well, it would be a little bit more correct saying that it is the juxtaposition of these two. You put them beside each other. That would be more correct to say. So, but you can already infer everything else that I'm going to tell in the next 5 minutes from that information. And that means if that is true, this means that this expression here, and by the way, the function application is left associative as an operator, so there is implicitly like parentheses here. So that means that times is a function which is applied to the number 2. What is this expression evaluating to? Well, since it is juxtaposed to the 3, it must evaluate to a function. Okay. So this must be a function that we later apply to 3. Hey, you're Haskellers. Oh, cool. Freak is. So if we ask the times, it actually tells us this. It says this arrow means we have a function from here to here. And functions always have only one argument and exactly one argument. It says, well, times here, is a function that takes an argument, this one, and returns, as we have seen, it returns a function which takes another a, which is number 3, and returns 6. So this is how you read it. And on the left-hand side, this is called a constraint. You can read this as a Java interface. That since we use times over here, that only works for numerical values. So-called type class over here. But I skip a little bit over that one. So if we look into these times too, since we already know that this expression denotes a function, thank you, we can reference it. We can use times2 and give it a name. Now, what can we do with that name? Well, we can apply it to some number, giving us 6. If we ask for the type of 2 times, what will that be? There's a number of options what could happen. It takes int to int. It's a function from integer to integer. Why not num to num or something? Because we have already specialized it to an integer, right? No longer can 3 be a double or a float or anything, because we have already specialized it. And these types must be the exact same types. They were both of type alpha, right? Therefore. Now, you may notice this space over here, and this space is there for a reason. If you think in Java terms, from a Java perspective, and you compare this to a way that you do methods in Java, you would expect there to be a formal parameter that you call, right? For this argument, you would like to see a formal parameter in your type, right? You can actually think of such a parameter. You can imagine such a parameter if you want to. Let's say there would be an x. Then for calling times 2, we would also need to supply the x, right? Is that okay? This is actually like in mathematics. This is like an equation in mathematics. You can extend an equation, but you also can cancel out terms of an equation. So if you, like in German, you say kürzen, right? You can cancel out the x. This is valid Haskell, including the gray ones, but you can cancel out the x. You can divide through x. That is the analogy, right? Actually, multiplication is applying a linear function in mathematics. So that is the analogy where that comes from. You can cancel out the x. That's the kind of operations that you can do on equations in all your Haskell code. Your Haskell code becomes, Haskell Frege code becomes a series of equations that you solve. And you can work with it like in algebra, which is, of course, not possible in any language that has statements or assignments or time. So these canceling out of these terms, I'd say, is sometimes called currying for good reasons, sometimes Schönfinkeling from Moses Schönfinkel, who did the theoretical work on this. But actually, this kind of concept of having functions that are used as arguments to other functions or being functions that are returned from functions is first described by Gottlob Frege, 1891, in, what was that, he did so many publications. I cannot cite the correct one. On concept of numbers or something. It was not in the concept notation. I have to look that up. I forgot that. Anyway, maybe not so important. So, infer times are more specific. And then we can also do function composition. So we have defining a function, using a function, applying a function, using parts of a function, and now combining functions. So let's say we do something like 2 times of 3 times 2. Well, as a Java programmer, I would assume that this now does the following. It would apply would evaluate 3 times 2, giving 6, and then applying 2 times to 6. That's like the Java way of doing things. That is called strict evaluation. You always first evaluate your parameters in a certain order, mostly left to right in most languages, and then you apply it. This is not the case in Frege and Haskell, because at Frege and Haskell they work lazily. They only evaluate this if needed. And there's a good reason for that as well. So, but anyway, this returns 12 as we expect. But we can write this in a different way as well. So the 2 times and 3 times are functions, and we can compose these functions into a 6 times. With these dot in the middle. And this dot is, let's get some help for this. And 6 times 2, we can apply this and get the type of 6 times, which is int to int, of course. Let's get some help for this. This over here is like a function f applied to the result of a function g applied to some x, right? The mathematical notation, you may remember this from high school. And your high school teacher may have mentioned that you can write this as the f composed g. Is that correct? Yes, correct. And apply to x. So this term here is a new function. This is our 6 times, right? You can actually do the same trick that we did before. You can put the x in again. You can put the x over here, 6 times x, 2 times and 3 times, put in parentheses in the 6 over here. It's still the same code. Would still work. But we already canceled it out. So you can compose functions because they're first-class citizens in your language. Clear so far? Questions so far? Good. So all this works only because we have pure functions. And since we have a lot of Haskellers in the room, you know, like 2 months ago, we had the Frege Day at Canoo in Basel. And we did a lot of interviews. And every interview at some point, especially when I asked, why are you here, what is special? And they said, at some point they said, you know what, it's pure. And you could feel the shot of endorphin going through their body when they say pure. And as a Haskeller, I would say it's not endorphins, they have a shot of endomorphisms. So. Good. So why do we care about purity? Well, if we have a Java method under any name, and we see the type signature and no implementation, and we don't trust the comments, what could we tell about any method from its type signature? Well, let's say type signature says, I take a pair of t and u and I return something of type t. What is that doing? Well, most likely it returns the first element of the pair. Could it return null? Yes, of course. Could it throw null pointer exception? Yes, of course. Could it print to standard out? Yes, of course. Could it log? Yes, of course. Could it go to the database? Yes, of course. Could it read from the database? Yes, maybe. Could it start the missiles and start Third World War? Of course, right? Who cares? In Frege or in Haskell, if you have this kind of type signature saying, I take a pair of alpha beta, I return alpha, for every computation that finally halts, that finally returns, the only possible implementation of that is returning the alpha. Nothing else can possibly happen. First, there is no null, which means there's also no null pointer exceptions. If there would be any kind of side effect, like reading, writing stuff, so it would be visible in the type. So, long story short, everything can happen here. You know exactly what happens here. This is a kind of type signature where actually a tool can infer the one possible implementation of the method. There's actually tools that do it, if you want to. It's not possible for every function to do that. Okay. With a pure function, once we have convinced ourselves that we have a pure function, and it is, of course, possible to write pure functions in every language. You can do it in assembler if you want, right? It's your developer discipline of doing it. In Frege or Haskell, we have the type system of telling us whether it's pure or not. And because the type system reveals that information, any tool, especially the compiler, can use that information. If we call the cosine function with 1.0, it returns 0? I don't know. Something. Okay, if we call it again with the same value, it will return the same value. You can memorize this. You can cache it. Since there is no notion of time anyway in a pure function, you can evaluate that at any time before it's used. You can do it lazily. You can do it in advance, speculatively, when the computer is idle anyway. Well, let's evaluate some expressions. You can do it concurrently, which is the big thing about concurrent programming and parallel programming. without any fear of deadlocks and race conditions and whatever. If you have code like times 2, 3, times 2, 3, times 2, 3, times 2, 3, the compiler, or maybe your IDE, can say, well, let's remove it and refactor it in one term that we have in the beginning. This is what you can only do with pure functions. If you had an impure function with a side effect, let's say system current time millis, here, 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 you wouldn't want to refactor that out, right? Certainly for a reason that you get the time at a certain evaluation point. So you can eliminate common sub-expressions, and all this is an optimization issue. And actually, this opens in a huge range of possible refactorings that the IDEs could now apply safely. Most refactorings from the IDEs that you get from your IDE at the moment as a developer are not really safe. That's more like a proposal. We suggest you could refactor this out into an extract method or something. You know, it's not really safe as long as you cannot ensure purity. But now it could be safe. It could be marked as, here's a safe one for you. Please ask your IDE vendor for supporting this. This is optimization that the tools can do, but also that the developer can do. Now, you may have found yourself in this position where you have some method. It may contain a bug, and you're not quite sure where the bug comes from some state change that shouldn't be there. Or you consider, where's that stage actually changed? Or can I refactor it? Or can I call it, is it thread safe? Can I call it in parallel? And you just don't know. So what do? You look into the implementation. And the implementation says, well, it calls A and B and C. And then you go into the implementation of A and then inspect this and then into B. And B calls A, B, C, B, D, B, Z. And finally, you end up like so. This is from an actual project. So you have to inspect around, and this is only one branch of the tree. It's actually worse in reality. So, and after a week of inspecting the code, you have convinced yourself, that's safe. I can call it parallelly. And you do it. And then the next day, some programmer of your team comes and changes, let's say, here. And does system out println because he needs it. Which, by the way, totally undermines all your parallelism because that synchronizes on the output stream and so on, right? So whatever the effect of that may be, maybe only performance drop or whatever. He has no chance of knowing that you made this silent assumption. You have no chance of knowing that he has broken your silent assumption. It's all full of silent assumptions, and this is the cause of bugs. How to get around this? Manual inspection doesn't work. So the only thing is we can ask the type system. If the type system tells us and keeps it in place that all this is pure, then we don't have to inspect it anymore. We can ask the type system. Well, I have to go one back. And type system. Now, pretty much every language on the here comes, now the next 5 minutes, comes the big difference of Frege between all other JVM languages. A unique point of Frege that I've not seen in any other language so far. And it comes from this point. Here, let's say I have a super duper language. It ensures purity through the type system. Here in this code, well, with the type system. But down here, or somewhere, maybe somewhere more up the call chain, is a call into Java. I call into Java. Oh, system out println, current time millis, whatever. Some Java method. Pretty much every JVM language goes the route of saying, well, as soon as you call into Java, all bets are off, right? Your fault. Well, it doesn't help so much, right? Frege goes a different route. Frege says, well, we do not combine on that level. we make a very clear distinction between our purely functional world and the object-oriented, well-established, imperative Java world. We make an extremely clear distinction. We can call both ways, but we do not mix. We do not mix the two paradigms. We keep our side clean. If you want to call from Frege into, from Java into Frege, that's the easy part, because Frege compiles to Java source code. It generates Java source code and then uses Java-C to compile it to bytecode. So you have Java source code laying around. Well, this you can call from any Java module anyway. So that's Java to Java, actually. Fine. If you want to see what kind of Java code it generates, you can even ask the REPL for give me the Java version of this Frege code. From Frege to Java is the interesting part. Well, now we have to distinguish, we have to declare, and we have to, it's not optional, we have to declare our silent assumptions about what the Java code is doing that may be hidden in the implementation or maybe in the API doc, whatever. Our assumptions become explicit. We have to declare explicitly what we think the type of the Java method would be in Frege terms. So, for example, JavaNet URL encoder encode is a static function. You may know that. And it is string to string. You give it a string, it returns a string. The string is immutable. It does no side effects. Only works on the parameters. It is pure. I can call it now from Frege as encode. This is the method that I assigned to it. Say Dierk König, and then it replaces blank with, I don't know, %20 or something. Fine. All nice and tidy, right? Everything is still pure. When I use this method, when I use this function, my code is still pure. We have other methods, and actually most methods are impure. Let's say poster child is current time millis. It takes just like a dummy parameter, if you want, and returns, well, this is a long in Java, but we say, well, it's not only a long, it's an IO long. And this, because now the long is somehow tainted, it's dirty. If the type system now knows that this is a dirty one. And IO long is actually more like in action. It's not the long itself, it's the action that would give you the long. And I can call the millis by just giving it the unit. But if I would like to, if I want to call it, I must be dirty. It makes myself dirty. But especially if I want to kind of do arithmetic with it, this does not compile. It says, millis is not a long. You cannot calculate with an IO long. First, you yourself have to become dirty. You have to taint yourself with IO. And then I would give you the long, and then you can do whatever you want to do. But it will make you dirty. So the caller gets dirty. And everybody who calls me will also get dirty. And him and him and him until main. Main is, of course, dirty. It does something. Yeah? It's not heating up the CPU. It's doing something. So that is the key distinction between to all other languages on the JVM. Actually, that was the point that sold me on the project. When I saw this, I thought, like, there's somebody who knows what he's doing. So, long story short, you can, from Frege, call into Java, but it's kind of an intimate thing. Don't do it unprotected. So second thing that you now get is that you have a global type inference, since you have no statements and no assignments and no control structures. From this, and this is difficult to reveal in these 50 minutes, from this you get an amount of structural safety about your code. The code is actually like it was knowing what you're doing and don't let you break out and use things in uncertain contexts and so on. So it knows structurally very well what you're doing and guides you to correct solutions. So you have much more safety, and for very little, for a very small price. So if you don't want to pay any price at all, you just don't do anything in the type system, right? You still get the type safety. And here is how you're going to use it. It is all your pure computations are like islands in a sea of imperative code, in a sea of dirty code. You have things that are mutable in your maybe Java, even Java-based application, and that does I/O and mutable I/O and databases and whatnot. But inside, you have islands of pure computations that where you can reason about equationally. That's the idea. And the type system ensures that once that somebody is dirty, he cannot escape anymore. It is like a context that you cannot escape. And in the first part, those are thread safe by construction. And if you have any error in your multi-threading or parallel, whatever solution, you can exclude a huge number of possible errors. You don't have to look inside those because they cannot fail. And then, like, technically, these things over here are called monads. However, get over it, it's just a name. And I'm going to show you some live coding. I guess we will maybe do a little bit, I may need a few minutes more than 50. And this is the FizzBuzz problem. Who has ever heard about FizzBuzz? Almost everybody. So you count numbers, and for every third number you say fizz, and for every fifth number you say buzz. And then you're counting from 1 to 100 like this. It's very often an interview question in job interviews. Some people say it's a children's game. Some people use it as a drinking game. Anyway. And if you ask on the internet for possible implementations of that, here is hit number 1. This happens to be an imperative code, and it's Java, but the point is not that this is Java. There's much better solutions in Java as well, but this is kind of the conventional way of writing it in Java. And the point is that this is typical imperative. You can write this in C. A C solution would also be like so. You have a for loop and lots of changing state, and then you have to think about, the point where 3 and 5 comes together. This is as at 15, and we have to cover this case first, and then comes the other two other cases, special cases, and then comes the general case. And okay, that's kind of typical code. Who would have written this kind of code to solve the problem? Oh, at least 2 or 3. Very good. Last time I asked at Devox, nobody was. And that was a lie, of course. Okay. So that is kind of the conventional way. And as I thought, the idea about a new language is it should make you think differently about the problem and a possible solution. So let's say if we call the Frege REPL, this is JavaFX. I'll make this a little bit bigger, Command B. This is written in Frege. It is using JavaFX GUI components. Anyway, so the first thing is we have no for loop. Yuck. Okay, we cannot do this. Go home. Okay, what we can do is we can use like a stream, an infinite sequence of numbers. This is something that we have available, and it is denoted like so. 1 ... And if we evaluate this, it gives us all natural numbers, whereas the REPL is intelligent enough of not giving us all natural numbers. But because of lazy evaluation, we can actually limit this. Okay. Anyway, it's automatic. Well, we need those since we want to print it not as the number, but as the string. So we're taking this and we are mapping every single element in its to-string representation. We're mapping this. And then on Frege and Haskell, it's called show instead of to-string. And we're taking this one dip. We see this as strings. Is that visible from the back? Is that? Yeah, okay. So, and we give it a name. This is the numbers. Okay, let's again check. Numbers is a list of strings. Good. Numbers is this. Now we need some kind of notion where we say every third is a fizz. Okay, how can we do this? Well, we have a list. It is an empty string and an empty string and a fizz. Okay? And if we want to have an endless repetition, an infinite repetition of that, we can say, well, please cycle over it. Give this did a fizz, did a fizz, did a fizz, did a endless rhythm. Cool. Let's give it a name. The fizz is that. How about buzzes? Well, you already know the trick. We make the same for buzzes. I could use a repeat here, but anyway, make this a bit easier. Buzzes. So what are the buzzes? Buzz, 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 buzz. Well, but the requirements say we have to kind of combine fizzes and buzzes. This is business rules, right? And if they come together, the fizzes must come first and then the buzzes, like if there's some kind of overlap. So we make ourselves a pattern from this. We have two infinite productions of strings, and we combine them element-wise. Zip, 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 zip. And it's called zip, like a zipper on your pants, right? So this is our pattern. Equals. It's called zip, and we are zipping it with a function, therefore zip with. And the function that we use is string concatenation, which is denoted by plus plus. And we're using the fizzes and the buzzes to do that. So what is the pattern? Did it a fizz, a buzz, a fizz, a buzz? And number 15 is FizzBuzz. So far, so good. But now about the numbers. We have to bring the numbers in. And okay, we can also zip the numbers, but what is the function that we can zip the numbers with? Well, here comes a little trick that I did not do in the initial version of this, but which was contributed by Kevlin Henne. And it has a nice observation, and it is strings have an ordering. And the empty string is always considered the smallest. And then come strings that only are composed of digits. And if you have any string that starts with a non-digit alphanumeric character, this is considered higher than those. Right? So you can use the maximum function. This is kind of interesting. So the actual FizzBuzz is the zip with the maximum function of the numbers and the pattern. Got it? That looks like, business process something. Business process modeling or so. Okay, so what is FizzBuzz? Here we have the first so many, right? But since the original statement was we have to print the numbers. So what we have here, it looks like an infinite list. But of course, there is no infinite list. There's nothing that occupies all our memory or so. That's not the case. It is actually more like an iterator, like a lazy sequence, like a stream. All those things are the same in lazy languages. So what we can do, we can actually iterate over that long stream. And now, what is the function name that takes an infinite production of things, an iteration over things, and applies some logic to it? How's that function name? Map would apply element-wise. I want to produce an effect, right? Println. I want to print something out. Apply could be one. For. Because it's actually the same thing as a for loop. For FizzBuzz println. You see? Yeah? I get goosebumps when I write this. How nice is that? So actually, FizzBuzz would be nice, but this would be an endless production of printlns. We have to limit this, right? So we have to limit it. Let's say we only take the first, take 100 of those FizzBuzz entries. Keep calm, keep calm. We actually be running out of time. So I take some liberty, and since the organizer granted me an additional 10 minutes, I'll do that. Okay. As long as nobody's leaving early. So I'd like to interpret this result a little. So you'll find that in the download as well. It's in the slide deck. So, but if we look into this two operations, you will see that the imperative solutions has 4 conditionals, 4 conditionals that we have to think through, whereas the logical one has 0 conditionals. Where do bugs creep in? In conditionals, particularly in nested conditionals. And the nesting level is, if you do the if-else and for, the cyclomatic complexity is 3, and here it is 0. The number of operators is 7, and most implementations actually have a little bit more because they do not use the 15, but they do 3 and 5 and so on, so it's actually more. And here we have the plus plus on strings, which we actually use as a function and not as an operator, but I give you that one. Okay, wouldn't want to argue over that. The sequencing here is extremely sensitive to reorderings. Almost any reordering of these lines will make a wrong solution, right? You can change the 3 for the 5 over here, but this is the only change that you can do. Every other reordering is wrong. Here you can, every permutation of these lines is correct. And by the way, have you seen the following? When we worked in the REPL, at no point in time did I go back and change anything that I had written before. At no point in time do I even have to recompile what I have written before. That is incremental programming, right? If you're not changing what you have written before, and you don't even recompile what you have written before, what can you break in the old code? Nothing. That is big. How do we write code? 1 line at a time, incrementally. And we only have to check that this line is correct. How cool is that? In the other case, every single change, every single increment that we want to do, we cannot do this non-intrusively. We have to do it intrusively. We have to change the old code. We may possibly break something. And this is not a thing that I kind of made up because I kind of choose exactly this example. It was like it came by total accident. But what I've shown you interactively was exactly the steps that I went through when I did it the first time. It's just the natural thing to do, and it turns out to have all these nice characteristics. And now comes maintainability. So customer comes. I see Stefan Rauch over there. So he is the expert on that one. So customer comes and says, well, you know what? Every 7th number should be GOTO conference. Oh, God. Now I have to care for the multiples of 3 and the multiples of 5 and the multiples of 7. And the multiples of 3 and 5 and 7 and the multiples of 3 and 5 in the correct order. Oh no, I forgot the multiples of 5 and 7 because it was too complicated. try to get this right. It's extremely difficult, and you have to touch everything that you did before. What do I do here? There is GOTO conference business rule that I also zip in. Done. Right? That's it. So maintainability is really bad in the imperative code, and it's natural, easy in the logical code. So the kind of to sum up the long talk, what we get when we don't have assignments, no statements, no control structures, only expressions, we get, and this is only possible in a purely functional language, so it makes a purely functional language, then we get global type inference. We can detect purity and use it to our advantage. We can use laziness, which is not possible before, and all the kind of separation of generating the infinite stream and using the infinite stream is only possible because of laziness. Otherwise, this kind of solution approach wouldn't work. And the guarantees that we have even extend into Java calls, right? We are not giving up our language guarantees. That makes us robust under parallel execution, robust under composition, robust under increments, robust under refactoring, and it is the best way of learning functional programming. If you want to learn English, go to England, speak English from dusk to dawn, the whole day long, and don't go to the native language anymore. For some time at least. That's the best way of learning it. It forces you into a new way of thinking. You will learn much more. And then it's just a pleasure to work with. I know everybody says this about his language, but here's true. If you want to learn it, you can just pick up any Haskell resource. There's thousands of tutorials and what have you, videos in all possible forms. You can pick those up, and then there's also any books or whatever. There's also a special free ebook for the specifics of Frege that you can check out. There's currently a massive open online course running by Eric Meyer for Functional Programming 101. I guess it's a little bit too late to jump on the train, but maybe then next year. It's a very good open online course. It's not easy, but it teaches you functional programming. That it is from my side. I'm very happy to take additional questions. And we have some, as I see. What happens when we wrongly annotate a Java method as pure?
Who decides whether it's pure or pure native?
Okay, who decides whether it's pure or pure native? You, as a developer, decide, but the Frege type checker will do some plausibility checks on what you say. So if you annotate something as pure, but it doesn't take any arguments, no matter what it really does in the end, whether it has a return value or not, if it doesn't take any arguments, it's very unlikely to be pure. Yeah? If it doesn't return anything, it is obviously not pure. It will not allow that one. It will give you warnings and errors in these cases. If you say, I'm using Java util time, and I'm not annotating this as so crazy as it is type-wise, you can change the time and so on. And, you can say 1st of October is now 2nd of October, whatever, in Java util time. If you do not annotate this correctly but wrongly, and it happens that somebody actually changes the value, you may see an outdated value then. Somebody changes the value, but Frege has cached it, so you not see the updated value. That will be the effect.